I'm going to give you an overview of the main components on a PC motherboard, an understanding of which might help you to make the right choices if you're buying a new PC or thinking about building or upgrading one yourself. This information is also essential if you want to go on and learn more about the individual components. PC architecture is evolving at an incredible rate, so it can be hard to keep up with developments. Deciding what does and what doesn't matter is no easy task, especially with all of the baffling jargon that's thrown around, much of which, quite frankly, is misunderstood and misused. For that reason, I'll spend a few moments setting the scene with a historical perspective. Until about 2008, the central processing unit, that is, the CPU of a typical PC, was connected to most other components on the motherboard indirectly. The central processing unit included an arithmetic and logic unit, responsible for executing program instructions, a control unit, and a number of registers. A register is the smallest and fastest unit of memory that a CPU can access. The central processing unit was connected to a chip on the motherboard known as the North Bridge. This connection was via a set of parallel wires drawn onto the motherboard, known as the front-side bus. The North Bridge was connected to the dynamic random access memory, the DRAM, via the memory bus, and to the graphics adapter via a high-speed graphics bus such as PCI Express, which stands for Peripheral Component Interconnect, or AGP, Accelerated Graphics Port. The North Bridge included the memory and graphics controller circuits, and was therefore often referred to as the Graphics and Memory Controller Hub. The North Bridge was also connected to a chip called the South Bridge via the Direct Media Interface bus. The South Bridge was in turn connected to the slower components such as the input and output devices, keyboard and mouse, the hard drive controller, the network adapter, USB ports, and so on. For that reason, the South Bridge was often referred to as the input-output controller. The North Bridge and South Bridge were so called because of their position in relation to each other, depending on your perspective, of course. The North Bridge and South Bridge were collectively referred to as the chipset. These days, the architecture of a modern PC is somewhat different. For a start, the CPU is likely to have multiple physical cores. 2 or 4 cores is common, but 8 or even more will soon be the norm. Each core has its own arithmetic and logic unit, its own control unit, and its own set of registers. So each core is capable of executing program instructions independently. If the software you're running has been written to take advantage of multiple cores, then doubling the number of cores will roughly double the rate at which instructions are executed. A modern CPU also has a rather large amount of high-speed cache memory. I'll say more about the way this type of memory is organized in a moment. Another significant change to the overall architecture is that the North Bridge chip no longer exists. The memory and graphics controllers are now integrated into the CPU chip. This removes the need for a front-side bus between the CPU and the RAM, which has had a huge impact on the performance of modern PCs. The South Bridge is also gone. It has been replaced with a single chip, which is often referred to as the chipset. The so-called chipset serves as a hub for controlling the slower devices connected to the computer. The chipset is connected to the CPU via a high-speed bus called the Direct Media Interface, DMI. If you buy a motherboard, it will most likely come with a chipset on it. The chipset dictates what type of CPU you can have, and because the memory controller is built into the CPU, this dictates the type of DRAM you can use. You can't just mix and match chipsets, CPUs, and DRAM. They have to be compatible with each other. Keep this in mind if you're planning to build or upgrade your own computer. The motherboard also has a crystal oscillator on it. An oscillator contains a quartz crystal that vibrates very quickly when an alternating current is applied to it. The frequency of this vibration is almost constant. The crystal's vibration is converted into a varying output voltage that changes from high to low and back again 100 million times a second, a frequency of 100 megahertz, as shown on this chart of voltage against time. This means the time for one cycle is 10 nanoseconds. This is called the base clock frequency because the oscillator sets the tempo for many of the computer's components, including the CPU. Special circuits inside the CPU, called frequency dividers and frequency multipliers, take this reference signal and multiply it up to a much higher frequency that can be used to control the rate at which instructions are executed. For example, multiplying a 100 MHz base clock signal by 35 will give a frequency of 3500 MHz. That's 3.5 GHz, which is a typical CPU clock frequency. The time for one cycle at this rate is less than a third of a nanosecond. A modern CPU might dynamically change its clock speed, depending on the task it's performing. For a demanding task, it can temporarily raise the clock frequency to get things done quicker. It can also throttle down the clock frequency if it starts getting too warm. A good cooling system will allow the CPU to operate at higher speeds for longer. Within the same brand and generation of CPU, a processor with a higher quoted clock speed will generally outperform one with a lower clock speed. Some types of CPU, however, can execute more instructions per clock cycle than others, even from the same manufacturer. If you compare an Intel K series with an Intel X series, for example, you may find that the later model outperforms the earlier one, even when running at a slower clock speed. Comparing CPUs from different manufacturers is even more problematic. The architecture of an Intel CPU is quite different from that of one made by AMD, for example. When it comes to processors, to compare like with like, you need to multiply the clock speed by the number of cores and by the instruction rate of each core. If a CPU's frequency multipliers have been unlocked, then it's possible to change the way the base rate is multiplied up by the CPU. This is called overclocking. Be warned, however, if you're going to try this, you might consider upgrading your CPU's cooling system first. Even then, other devices in the PC might not be able to keep up with an overclocked CPU, which can make the whole system unstable. Some PCs allow you to change the rate of the base clock, but getting this wrong can be disastrous. Other computer components can run at different rates to the CPU cores by dividing or multiplying the base clock frequency according to their own needs. Multipliers inside the memory controller can generate a different frequency to control the rate at which data move on the memory bus, for example. A memory bus designed to support DDR4 DRAM typically operates at a frequency of about 1.2 GHz. Some PCs allow you to overclock the DRAM as well as the processor. Now let's take a closer look at the CPU cache. Cache memory is essential because the CPU can execute instructions and handle data much faster than they can be read from or written to the DRAM. The cache therefore serves to keep the CPU fully occupied while instructions and data are copied to and from the DRAM. Cache memory is much faster than DRAM because of the technology used to build the cells that store individual binary digits. Cache memory cells are flip-flop latch circuits which can be accessed very quickly. They also retain their contents as long as they are supplied with power, which is why this type of memory is known as static RAM or SRAM for short. The memory cells in DRAM, that is dynamic RAM on the other hand, are based on capacitors. DRAM cells leak their charge very quickly and therefore need regular refreshing. But DRAM cells are smaller and cheaper to manufacture. The CPU's cache is arranged in levels of increasing size but decreasing speed of access. Each core has its own level 1 cache. This is the quickest level because it's closest to the core, but it's also the smallest. Typically, the level 1 cache has a capacity of 64 kilobytes and an access time of between 1 and 2 nanoseconds. The level 1 cache is divided into two, one half for program instructions and one half for data. This allows instructions and data to be accessed independently, making the level 1 cache even more efficient. Furthermore, the level 1 data cache has to deal with read and write operations, but the level 1 instruction cache only needs to handle reads, allowing for simplified circuitry. Each core has its own level 2 cache, which is shared by instructions and data. A typical capacity for the level 2 cache is 256 kilobytes. The access time is between 3 and 4 nanoseconds. The level 3 cache is much larger and slower. It too contains instructions and data, and it's shared by all of the cores. This has a typical capacity of 6 megabytes and an access time of 10 to 15 nanoseconds. In contrast, the DRAM in a typical PC has a capacity of 8 gigabytes and an access time of 50 to 60 nanoseconds. Now, let's suppose the CPU wants to retrieve something from memory. Let's say, for example, a program instruction. The memory address of the next instruction to fetch is stored in a register called the program counter. The CPU checks the level 1 instruction cache first. If it finds what it's looking for, this is called a cache hit, and the instruction is copied into one of the CPU's registers. In the event of a level 1 cache miss, the level 2 cache is checked. If this is successful, the instruction is copied to the level 1 cache and then into one of the CPU's registers. If there's a level 2 cache miss, the level 3 cache is checked. If this results in a hit, the instruction is copied into the level 2 cache and the level 1 cache and then a register. Only if there is a level 3 cache miss does the processor go to the DRAM via the memory bus. The requested instruction is then propagated back through the various levels of cache to the CPU. But program instructions and data are not copied around one at a time. Cache memory is divided into cache lines, with each line typically containing 64 bytes worth of instructions or data. During a data or instruction transfer, the entire cache line is read or written in one go, even if the whole line isn't needed. This works well with programs because chances are the next instruction that the CPU needs is right next to the previous one. This is called spatial locality. Data can also exhibit spatial locality. An array variable, for example, stores data in contiguous memory locations. Programs with looping constructs can benefit enormously from caching, because the same set of instructions are executed repeatedly. This is called temporal locality. Programmers with a good understanding of caching often write very efficient software. Saving data in the memory via the cache is similar to retrieving it. The level 1 cache is updated first. If the level 1 cache is getting full, an entire cache line is copied into level 2. When the level 2 cache needs more room, an entire cache line is copied into level 3. Finally, if necessary, an entire cache line will be copied to the DRAM. This means that data and instructions are never copied individually to or from the DRAM. They are always transferred in bursts of at least 64 bytes. To summarise, the central processing unit can have multiple cores. Each core has a control unit, an arithmetic and logic unit, and various registers. The memory and graphics controllers are built into the CPU of a modern PC. The base clock frequency is provided by a crystal oscillator on the motherboard. Different components can divide and multiply the base clock frequency as needed. The CPU can adjust its clock speed dynamically. The CPU cache is organised into 3 levels. Data move between the cache levels and the DRAM in cache lines of 64 bytes. I just want to show you some information about my own PC, which I'm getting from a little utility called CPU-Z. You can download this for free. Notice the bus speed, which is just under 100 MHz. This is actually the base clock frequency coming from the crystal oscillator. I can also see here that it says multiplier, which is around about 34-36. Remember, the CPU can dynamically adjust its clock speed. So if we multiply this value, about 100 MHz, by 33-34, then I get the core speed. You can see this is about 3.4-3.5 GHz. And because I've got 4 cores in this machine, that's multiplied by 4. If we take a look at the caches tab, I can see here I've got my level 1 data cache, my level 1 instruction cache, level 2 cache, and my shared level 3 cache. And you can see the capacities of each. We're looking at 32 kilobytes for the level 1 data cache and 32 kilobytes for the level 1 instruction cache. There's also some additional information about the memory here. Now I can see the DRAM frequency is around about 1063, 1064. This is the speed of the memory bus, and again you can see it's changing, it's fluctuating. I've actually got 2 memory buses inside this computer, which means that I can have 2 DRAM chips operating independently. This is called dual channel mode. You may be fortunate enough to see quad channel mode there, which means that your memory will be even faster. This number here, a ratio of 1 to 16, tells me how the base clock frequency is being used to produce the DRAM frequency. In fact, the base clock frequency is first divided by 3, and then it's multiplied up to produce this number. It's called the front side bus to DRAM ratio, but of course there is no such thing as a front side bus anymore. These numbers you can find out more about if you study DRAM in more detail. They tell me how long it takes for the memory to start delivering data when the CPU asks for it. They're measured in clock cycles. So for example, it takes 15 clock cycles for the so-called CAS latency. This is a bit like when you turn on a garden hose. You don't get water coming out immediately, but once it starts to flow, everything's fine. Suffice to say, the smaller these numbers, the better.